Welcome to General Chemistry Mini Lecture Series, Lecture 20, Classification of Chemical Reactions. So we are mainly talking about classification of inorganic reactions in this lecture. There are so many types of chemical reactions. The important ones are acid-base reactions. We also call that neutralization reactions, precipitation reactions, oxidation reduction. We also call that redox reactions. So the first three are the most important ones. Then after that, of course, we also have gas formation reactions, hydrolysis, single replacement, and double replacement reactions. First, let's talk about acid-base reactions. Strong acids with strong bases produce salts and water. Take an example. Nitric acid reacting with sodium hydroxide forming sodium nitrate and water. This one is the molecular equation for this reaction. Okay. All reactants and products are written as if they were molecules, even though we know actually, for example, NaOH exists in aqueous solution as a sodium ion and hydroxide ions, so separate ions, not really together. But when we write them together, then such equation, we call that molecular equation. The driving force for this reaction is actually the formation of water. That's very important. The phase indicator here for water should be L. Now, complete ionic equation or total ionic equation. So for this same reaction, nitric acid in water, AQ again means in water, so breaks down into hydrogen ion, nitrate ion, sodium hydroxide, sodium ion, hydroxide ion, sodium nitrate, sodium ion, nitrate ion. Water, it stays together, okay? So it does not ionize. So therefore, this is the only one that does not break down into ions as the others. So this is called complete ionic equation or total ionic equation. And now you see there are spectator ions. What are those? For example, nitrate. It appears on the left-hand side, also the right-hand side. So is the case with the sodium ion. Sodium on the left-hand side, sodium on the right-hand side. So those are the spectator ions. They do not participate in the reaction. So therefore, after we cancel those spectator ions, we will obtain the net ionic equation. In other words, after canceling those spectator ions, the total ionic equation becomes the net ionic equation. So in this case, we only have hydrogen ion reacting with hydroxide ion forming water. Titration is the process of determining the unknown concentration of one chemical that reacts with another chemical solution, but with known concentration. So through stoichiometry. The one with unknown concentration is generally called analyte, and it is placed in an Erlenmeyer flask normally. The one with known concentration is generally called titrant and placed in a burette. So during a titration, the titrant solution is added to the analyte until the reaction is just completed. At this point, it's called the equivalence point. Then the two reactants are in their stoichiometric ratio that is used to determine the unknown concentration of the analyte. One of the challenges in titration is that it's impossible to accurately measure the equivalence point. So therefore, indicators are used in titrations so that when the titration reaches the equivalence point, actually the indicator is supposed to change colors. When the indicator changes colors, we call that end point. The closer the end point to the equivalence point, the more accurate the titration is. When the titration approaches the end point, it is vital to add the titrant very slowly to the analyte flask to avoid missing the end point. Normally that would require drop-wise titration, even half drop. So these slides demonstrate the titration between hydrochloric acid and sodium hydroxide. Sodium hydroxide is titrant in the burette. Hydrochloric acid is the analyte and is placed inside an Erlenmeyer flask. So this one shows the start of titration. You should have excess of acid because you just started the titration. So mainly you still should have plenty of hydrogen ions in there. And this one is at the end point. No more acid and base. You should just have the salt and water in the flask. Then after the titration, when you further introduce sodium hydroxide into it, it should have excess hydroxide in the flask. And you see the color change. Before it reached the end point, no color change. At the end point should be pale pink. After the end point becomes completely pink. Now let's talk about precipitation reactions. We have lead 2 nitrate reacting with potassium iodide, forming a precipitate of lead 2 iodide, and of course a soluble potassium nitrate. So the driving force for this reaction is the formation of this precipitate. This equation we call that molecular equation because everything is written as if it were molecule. Total ionic equation. So this is an aqueous solution that should break down into lead 2 and nitrate ions. Another aqueous solution that should break down to potassium and iodide. Lead 2 and iodide, they stay together. We cannot break them down to individual ions. And then potassium nitrate also breaks into potassium and nitrate ions. Okay, and make sure when you write down the complete net ionic equation, that also need to be balanced, which means you have to take care of the coefficient. You see, there's one lead, and then 2 nitrate, 2 nitrates, 2 potassium, 2 iodide, 2 iodide, and so on and so forth. Now, after canceling the spectator ions, you see the net ionic equation for this one should be just lead 2 reacting with iodide, forming lead 2 iodide precipitate. Redox reaction. Iron reacting with oxygen, forming iron 3 oxide. That's the molecular equation. When atoms lose electrons, we call them oxidized. Iron in this case is oxidized because lost electrons become iron 3 plus. Okay, so therefore losing electron, oxidation reaction, and iron is oxidized. If iron is oxidized, itself is the reducing agent. So oxygen, on the other hand, it gains electrons, then undergoes reduction reaction. So we say oxygen is reduced, and oxygen itself is the oxidizing agent. Look at another reaction. Each sodium atom lost 1 electron. So this reaction is oxidation reaction. Sodium is oxidized and sodium is the reducing agent. Chlorine, on the other hand, gained electrons, and we say this reaction is a reduction reaction. Chlorine is reduced. Then chlorine itself is the oxidizing agent. Gas-forming reactions. The driving force for this type of reaction is the formation of gas. There are several ways of forming gas. One way is formation of gas by ion exchange. The anion of sulfide from potassium sulfide combines with the cation from sulfuric acid, forming hydrogen sulfide gas. So that's a formation by ion exchange. Formation can also be formed by the decomposition of one of the ion exchange products. Okay, so you see this reaction yields a product of sulfurous acid, further breaks down to water and sulfur dioxide. That's a gas. And also some metals, when they react with water, like sodium reacting with water, forming hydrogen gas. They are all different types of gas formation reactions. Hydrolysis reactions. So that typically is a salt reacts with water, forming either a weak acid or a weak base. For example, sodium fluoride reacting with water, forming hydrofluoric acid, which is weak acid, and hydroxide. Potassium ammonium reacting with water, forming ammonia, weak base, and hydronium ion. Hydronium ion is the same as hydrogen ion. Single replacement reactions. So you see, in this reaction, the hydrogen atoms in hydrochloric acid, so they are replaced by the zinc atoms and forming new species, zinc chloride and hydrogen gas. Another example, sodium chloride reacting with fluorine. Fluorine replaces chlorine, and then it forms a compound with sodium. That's a sodium fluoride, and releasing chlorine gas. Double replacement reactions occurs when two reactants exchange ions, then form new products. And those reactions are typically also neutralization reaction, precipitation, and gas formation reactions. Okay, let's take a look at this one. Strong acid, strong base, but you see they exchange ions or double replacement. You see hydrogen replaces sodium. You see, so the hydrogen replaces sodium, hydrogen combines with hydroxide, forming water, and then nitrate replaces hydroxide, combines with sodium, that forms sodium nitrate. That's double replacement. This is another double replacement reactions, but this one is a precipitation reaction also. Here is the third example on this slide. In addition to the double replacement reaction, this is also a gas formation reaction. Here are the end of lecture 20 quizzes, and I'm going to work on number 3. Which of the following best describes what happens after mixing aqueous calcium nitrate with magnesium chloride solutions? Do we have a chemical reaction? Let's take a look. Calcium nitrate, that's aqueous solution, and then magnesium chloride, another aqueous solution. After exchange the ions, calcium, chloride, now we need to determine whether calcium chloride is a precipitate or not. So we need to use the solubility rules. Okay, chloride, normally they are soluble. You see, chloride are normally soluble, but they become insoluble when they form compounds with those ions. Calcium is not one of those ions, which means then calcium chloride is soluble. So therefore, that's AQ. Now, when nitrate and magnesium, when they pair, that should be magnesium nitrate. Is this one soluble? Is this compound soluble? Nitrate, always soluble. So therefore, magnesium nitrate is soluble. So we place AQ there. Now let's take a closer look of this reaction. Remember the driving forces for a chemical reaction? That should be formation of water. Do we see that? No. Formation of a precipitate. Do we see that? No. Formation of gas. Do we see that? No. And change of oxidation numbers. Do we see that? No. So therefore, there is no chemical reaction. And here are additional end of lecture 20 quiz questions. So I will see you guys in lecture 21.